Hello, today we are going to be talking about the fundamental counting principle and permutations. So we're just counting. And I know you look at that or you hear that and you think, counting? I mean, I've made it pretty far in math. I think I'm okay at counting. Well, we're going to be looking at some more challenging counting problems that do tend to stump people when they first see them. And hopefully as we work through these, they'll get a little bit easier. So the first thing we're going to do is we're going to use a tree diagram to show all of the ways in which a series of successive events can occur. This tree diagram is a nice way to visualize this. We won't use them often. You'll see why in a minute. Each branch of the tree shows the options for any particular choice, and then the total number of options possible can be counted along the bottom or the end of the tree. So let's look at making a tree diagram. Stevens is buying a new car and has narrowed the choice down to two models, a sedan or an SUV. Each model comes in three colors, black, silver, or blue. How many different car options are possible, and show all the possibilities using a tree diagram? So some people like to build their trees from the top down. I'll do that here, and then in the next one I'll probably build it to the side, which is how I usually do it. So to start out with, you can think of it like this. We've got a choice to make. When Stevens walks onto the car dealership, he can either get a sedan or an SUV. And he's going to walk in and it's an either or situation. He's not going to buy both. And then once he decides what kind of vehicle he wants, then he has to pick the color. And you'll notice that we have black, silver, and blue for each one of these. And now, if you were to follow this path, you can see all the possibilities that happens for Stevens. So he could walk onto the dealership and he could get a sedan and then black. That's one possibility. He could choose a sedan and then silver. That's another one. Or sedan and blue. Or maybe he walks over to the side that has SUVs and chooses a black one, or a silver SUV, or an SUV that's blue. So you can see in total, he has 6 possibilities. Now, hopefully, even before you looked at this tree diagram and you watched me do this, hopefully you kind of looked at this and said, wait a minute here. If he has 2 different choices for cars and he has 3 different choices for colors, I could probably just multiply those and get 6. And you would be exactly right. If you were to follow each of these uh, paths, you could get like a sedan black car, or a sedan silver car, or a sedan blue car. I'll use L for blue. Or you could get an SUV, which I'm going to use V, V black, VS, or VL. So those are all 6 possibilities. And yeah, it really is as easy as taking 2 times 3. Right? At each decision, what kind of car? You can see he has 2 choices for that. And then he has to choose a color. He has another decision, right? And he has 3 choices for that. And so just multiplying the number of choices that you have at each decision point will get you the total possibility. Let's look at another one here. This one I'm going to do sideways. Maya's ordering a latte at a local cafe, and she can choose between 2 coffee roasts, either light or dark. She can then choose 3 types of milk. So we have 3 types of milk. We have whole milk, oat milk, and almond milk. And then lastly, she can choose the type of syrup that she wants, vanilla, caramel, or hazelnut. Draw a tree diagram to represent all the possible latte combinations. Well, hopefully you can kind of look at this and say, listen, based on the last problem, we have 2 choices here, we have 3 choices here, and there's 3 choices here. I'm betting that it's going to be 2 times 3 times 3, which is 18. There's going to be 18 possibilities. And you would be right. But let's get a visual of that. So we're going to start out. I'm going to try to make as much room as I can here so we can get light or dark roast. And then after that, we've got the types of milk. We have whole milk, we have oat milk, and we have almond milk. And then after that, we now get to choose the flavoring that we want. And so if we choose a light roasted coffee with whole milk, we can then still have the choice of vanilla, caramel, or hazelnut. Or if we choose a light roast coffee with oat milk, we still have the choice of vanilla, caramel, and hazelnut. And we have that for all of these, vanilla, caramel, hazelnut. And this just shows you why we can just multiply these choices, because at each decision point that we have in our tree diagram, light and dark, well, there's two choices, right? It branched out twice. So that's 2. Then we go to the next branch. The next decision is the type of milk, and you can see we have 3 choices for that. And then we have the colors, not colors. Then we have the flavors. And there was 3 choices for that too. And so you can see we have our 2 times 3 times 3, which is our 18. Now, when you look at this, you're like, okay, tree diagrams, they get a little bit messy. Yeah, they do. Because you can follow any of these branches and be able to find one of your possibilities, right? If you were to follow, I'm going to choose light coffee with oat milk and then hazelnut. Okay, that's one possibility. Oops. Or you could choose dark roast with whole milk and caramel. That's one possibility. There's a total of 18 of them, and that's a lot. Just think if we had another thing, like whether you wanted whipped cream or not, or if you wanted sprinkles. Like these tree diagrams would grow really big, and they're just not convenient. Instead, we can kind of learn what's called the counting principle, and we can just multiply these number of choices. So in our tree diagram, each outcome from one decision splits into multiple branches for the next choice or for the next decision. And then the total number of outcomes is found by multiplying the number of options at each step. If one decision can be made in n sub 1 ways, and a second decision is made in n sub 2 ways, and so on, we're really just multiplying them. And I know that this is kind of a fancy math way of really just saying multiply the number of choices at each decision point. As we said here for the first one, when we look at we have the model of the car, that's our first decision point, and we had 2 models to choose from, and then we also had the color to choose from, which was 3. Ta-da! When we look at the other one, we had the roast, and we had the milk, and then we had the flavoring. So for our roast, we had light or dark, that's 2 choices. For the milk, we had 3 kinds of milk, and we had 3 kinds of flavoring. This is just so much faster and so much more convenient to multiply those than to make a tree diagram. So let's use that on some more practice problems here. You're planning your weekly gym routine and you need to choose 1 cardio class and 1 strength class. You have 12 cardio classes to choose from and 8 strength classes. Then these will all fit your schedule. How many decisions need to be made? Well, notice that we're going to choose 1 cardio class, that's 1 decision, and 1 strength class, that's a second. In total, we have to make 2 decisions. So what I'll do is put 2 blanks down, right? We have our cardio and we have our strength. Then what we'll do is identify how many choices we have at each one of these decision points. In this case, it tells us there are 12 cardio classes, so we'll put a 12 in here for cardio. And they also tell us that there are 8 strength classes. Oops. So we'll go ahead and we'll um, put our 8 in for strength. Now we're just going to multiply these. Remember, we take and multiply them as we go. So 12 times 8 should get us 96. There's 96 possible ways that we could get these classes to fit our schedule. When you go to buy a new phone, you have to choose between the model, the storage size, and the color. There's 2 different models, 3 storage options, and 4 color choices. Well, you can see what we have here is 3 decisions. So I'm going to put 3 blanks down, right? We have the model, we have the size, the storage size, and we have the color. Each of those blanks, I need to figure out how many choices I have for each one. It tells me there are 2 models, there are 3 storage options for the size, and there are 4 color choices. So when we multiply 2 times 3 times 4, that should get us 24 possible phones that we could get. The next one is a little bit different, just a little. Telephone numbers in the United States consist of a 3-digit area code followed by a 7-digit local number. Neither the area code nor the local number may begin with a 0 or a 1. Now, when we think about this, our phone, how many decisions need to be made? You might be tempted to say, well, we have a 3-digit number here and a 7-digit number, so it looks like 2. You only have 2 colors there. No, yeah, I know. There's 2 colors, but we have 3 digits. That means we're going to make 3 choices for that one, or I should say 3 decisions. And then when we go to punch the next 7 numbers, we got to make 7 more decisions. So that's a total of 10 decisions whenever you punch your numbers in on the telephone pad. So let's go ahead and put 10 blanks down. There's 3 for the area code. And then we have our local number. 1, 2, 3, 4, 5, 6, 7. This part is our local number. If there were no restrictions, when you go to punch the numbers in on the telephone pad, you might say that, well, I have 10 digits to choose from. I have the digits from 0 through 9 on my keypad. And it's just 10, 10, 10, 10, 10, 10, 10. I think that's all of them. And if there were no restrictions, that's what it would be. Because when you go to punch the first number, you can choose any number from 0 to 9. When you go to choose the second number, any number 0 to 9. The third one, any number 0 to 9. The problem and why this doesn't work is they tell us that the area code and the local number cannot begin with a 0 or 1. So that means I got to come back and look at this one, and I've got to look at this one here. I don't actually have 10 choices for those, because if I can't have a 0 or a 1, then that means I only have 8 choices left. Like, think about all the digits that we have from 0 to 9. If you can see we have 10 choices, but if I'm not allowed to use a 0 or a 1, then that leaves us with 1, 2, 3, 4, 5, 6, 7, 8. I actually only have 8 choices for the very first digit of the area code. And the same is true for the first digit of our local number. We only have 8 digits. See, the phone company has reserved 0 and 1 so as to alert that you're doing something different. When you hit 0, that's like the operator, and if you use 1, it's saying I'm dialing a long distance, right? I'm going to have a different number of numbers, so watch out for that. Then what we do is we just multiply these all together. I could do this by hand, and I can take 8 times 8 is 64. And then notice that I have, let's see, 1, 2, 3, 4, 5, 6, 7, 8. I have 8 of these 10s here. So 64 times 10 to the 8th. That would work. I can also write 64 and then just put 8 zeros down. Make sure to use commas whenever you start having numbers this big. It just really helps as you're reading things. So this is 6,400,000,000, it looks like. So these two are equivalent. I also do want to show you what this looks like on a calculator, though. So if I do multiply 8 times 10 times 10 times 8 times, and now I need 6 of these 10s. Okay, I think I got them all. You can now see that it's 6.4 times 10 to the 9th power. So 64 times 10 to the 8th, that's really close to scientific notation, but the proper way of writing scientific notation and how your calculator will do it is actually more like this, where the first number is some number between 0 and just less than 10. So you can see 6.4, so we just have one number in front of the decimal. And then however many times 10 to an exponent, however many places you're going to need to move the decimal. All three of these values are equivalent to each other, and I would hope you take a minute to understand why. Okay, so in the United States with this particular phone system, this is how many phone numbers are possible under these particular rules. Let's go to the next one. You're taking a multiple choice test that has 10 questions, and each question has 4 answer choices. You know, maybe it's like A, B, C, D, right? Well, if you have 10 questions, that means you're actually going to have 10 decisions to make, because you're going to go to number 1, and I'm going to put my 10 blanks down. There we go. When I go to number 1, I can choose from, A, B, C, or D. So that means I have 4 choices on number 1. And then when I go to number 2, you know what? I can still choose between A, B, C, or D. So I have 4 choices. And when I do number 3, I can still choose between A, B, C, or D. And hopefully you kind of see that's going to continue on, because it's possible to have a test where the answer choices go, A, B, A, C, A, D, however many more I need. I lost track. What we have here then is we're going to multiply these 10 decisions all together. And this then is just 4 to the 10th power. That's what 4 times itself 10 times is. So we'll just do 4 and then to the 10th. There we go. You can see we get a little over 1,000,000. That means that if you were to sit down and take a multiple choice test that has 10 questions on it, and each question has 4 choices, A, B, C, D, if you didn't even read the questions and you just guessed, you would have a 1 in a little over 1,000,000 chance of getting them all right. So there's 1,048,576 possibilities. All right, this next one's a little silly, but also kind of fun, because I know we've all been there, I hope. You've already written a message to someone that you have a crush on, and you feel very confident about what you have to say. However, once the message is written, several follow-up decisions arise. You have to decide whether or not to include emojis. Like, are you a playful person and you want to show that? So you have to decide if you're choosing emojis or not. Then you have to choose where to send the message. Are you going to text it to them, or are you going to post it to one of their 3 social media accounts that they have? Then you've got to decide whether you want to include a GIF or not. Sorry, but those of you that are GIF or GIF, I'm all in on GIF. Okay. After that, you choose where to send the message. Sorry, when. Are you going to send it in the morning, the afternoon, or night? Because sending a message at 1 a.m. is very different. Like, even if it's the same message, it's very different getting it at 1 a.m. than at 1 p.m. So we have the choice of what time to send it. And then finally, you have to decide whether you're actually going to hit send or not. So let's go through and figure out how many decisions we have to make here. The first thing that we're going to do is decide whether or not to include emojis. So that's 1. Then we have to decide where to send the message. So that's 1. Then we have to decide whether you're going to include a GIF or not. That's one of them. After that, you choose whether or not to actually send the message. Sorry, when. I think I said that same thing last time. When you send the message, so the time of day. And lastly, whether or not you actually send it. So it looks like we have 5 decisions that we need to make. Let's put our 5 blanks down and we'll kind of label each of these blanks. We have emojis or not. Then we have where to send it. We're going to decide whether or not we want to include a GIF, and then the time, and then do we actually send it? Like, how many times have you had something all written out and then you just decide not to send it, right? That's a choice. So each one of these then is a do you include emojis, yes or no? Well, that means you have 2 choices here. Where do you send the message? This can actually be a little tricky because it says a text message or one of 3 social media platforms. That means you have 4 places that you could send it. You could text it to them personally, or you could send it to them on, whatever the 3 other social media like Snap or Instagram, Twitter, X, I don't know, whatever. I don't use any of them. Then we have to decide whether you're going to include a GIF or not. And again, this is a yes or no. So that means you have 2 choices. The time of day, there's 3 times of day that you could send it. And then lastly is whether or not you actually hit send. So if we multiply together 2 times 4 times 2 times 3 times 2, I think we get 96. And I'm just going to double check that. Yep, 96. Whew. That's a lot of decisions to make just over a silly little, hey, what's up? Right? All right. We're going to move on and look at some different notation with counting because counting can get to be a lot more complicated than what we've done now. But with some systems in place, we're going to make it easier, actually. So if n is a natural number, then n exclamation point, or n, is read as n factorial. And that's just the product of all the natural numbers from n all the way down to 1. I'll give you an example here in a second. The next thing that we're just going to write down is 0 factorial is equal to 1. I know that looks weird. We'll have an example later as to why that is. Basically, it's by definition, meaning this is what we're saying it is. Just know that it is. Okay. So the next thing we look at here is 3. No, just kidding. It's 3 factorial. And 3 factorial means 3 times 2 times 1. You just start with whatever the number that is and you multiply them all the way down to 1. That one's very easy to do. I don't even need a calculator for it. The next one, number 9, which of course would be read as 6 factorial, is how you would actually say that out loud. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. I've always liked to think that whenever they came up with this notation, they were just very excited that they could shorten the number down so quickly. Because if you have something like 24 factorial and you had to write out 24 times 23 times 22 times 21, that would be really boring. So we shortened it down with this factorial and they were just super excited to not have to write that anymore. By the way, that's probably not true. I just like to think that it is. So I can grab my calculator and do 6 times 5 times 4 times 3 times 2 times 1, and I get 720. Well, that's nice. But your calculator can actually do more than that. So if I grab this calculator back again, I can do 6, and if you have a keyboard, you can actually just hit the exclamation point and that'll work. But if you're not on a keyboard like me, there's an exclamation point right there, right at the bottom of my screen, okay? Just above this little arrow here. 6 factorial, notice that the calculator shows you that's 720. So your calculator will do this for you. Good news. The next thing is we have 8 factorial over 5 factorial. If we expand this out, 8 factorial goes 8, 7, 6, 5, 4, 3, 2, 1. And 5 factorial means 5 times 4 times 3 times 2 times 1. And we can go to our calculator, we could get that numerator and we could get the denominator and have it do it that way. But our calculator is pretty smart, especially if you're doing this Desmos thing. Because I can do 8 factorial, and then I'm going to use the divided by button, and then I'll do 5 factorial. And this just tells me it's 336. My calculator looks almost identical to what I have written, 8 factorial divided by 5 factorial. I do want to point one thing out though, and that is that if you didn't have a calculator, this could still be done relatively easily, because if I'm going to take 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 and then divide by 5 times 4 times 3 times 2 times 1, man, do I really need to multiply by 5 just to end up dividing by 5? And then multiply by 4 just to divide by 4 in a minute later? No, these reduce out because of numbers, these factors that are in the numerator are all being multiplied, and factors in the denominator are all being divided. So 5 divided by 5, some people say cancel out, but those will divide out from each other to just 1. 4 divides by 4, 3 divides by 3, 2 and 2 and 1 and 1. And so really, this just comes out to be 8 times 7 times 6. Whoops, let me get rid of that. I have a little, there we go, okay. 8 times 7 times 6. Yep, still get the same thing, 336. So if you didn't have a calculator, we could still do that. I realize I still multiplied it on the calculator. This little idea will come up in a little bit. Now, up to this point, we've used the fundamental counting principle in situations that are independent of each other, meaning that making one choice doesn't affect the options available to the next choice. Consider what we did with the cars, right? We had black, silver, and blue, and it didn't matter if you chose a sedan or an SUV. Okay, so those are independent. It doesn't matter what model you picked, you still have the same choices for the colors. It didn't matter whether or not you included an emoji or not. You still had all of those choices for the next one. Well, in some counting situations, however, decisions are dependent, meaning that once a choice is made, it changes the options that remain. When decisions are dependent, the fundamental counting principle still applies, but it leads to a special type of counting result called a permutation. Permutation describes a situation where a series of decisions must be made, and the order of those decisions matters, and the options cannot be reused once you use them. For example, if you're assigning 3 different students to 3 different time slots, first, second, and third, well, because a student can only present once, each choice removes an option for the next decision. For the first slot, there's 3 choices, and then 2, and then 1. So there's a total of 6 possible presentation orders, right? So if we have first, second, and third, and let's say we have, I don't know, Tim, Jane, and Sarah with an H. Well, once we pick the first person to go, maybe Sarah goes first, then what happens is she's no longer an option for the second position. She's already done her presentation. She's not going to go again. So that's why we had 3 choices for the first one, and now only Tim and Jane are left. So there's only 2 choices for the next one, and maybe Tim goes here. And then what happens is now there's only 1 choice left for the last one. Okay, so that's where we end up with 3 times 2 times 1. If you need to arrange 7 of your favorite books on a small shelf, how many different ways can you arrange the books, assuming that the order does make a difference? Maybe you want them in a very specific fashion. Well, what you think about is all the positions that you have. I have 7 positions on my shelf to put these books. And what I do is I have 7 choices for the first book, whichever one's like closest to me. And then once I put that in that spot, I only have 6 choices left, and then 5, and then 4, 3, 2, 1. Don't forget, we're going to multiply all of these 7 decisions together. Now, we could have shortened this down by saying 7 factorial. 7 exclamation, 7, right? 7 exclamation point. But a lot of people would rather write it like this, where we do 7 factorial and write 5040. Don't forget, that is the same as doing 7 times 6 times 5 times 4 times 3 times 2 times 1. So there's 5040 possible ways that you could arrange these books. Now, I do want to stress that word arrange, because almost anytime you see that, that's an important word. That means order matters. Another time, we'll look at what happens when order doesn't matter and you're just taking a group of things. But today, we're focusing on order matters. Well, what happens if not all of the objects are needed? You see, some decisions leave options unused. The fundamental counting principle shows this nicely, but the factorial method seems like it's incorrect. So let's look at a slightly modified example. Suppose there are 5 students, but you're only assigning 3 to do presentations. So when you have those 3 slots, right, I don't know, maybe first, second, and third, you have 5 different choices for the first person to go. So for the first slot, there's 5 choices. And then for the second slot, you have 4 choices, because whoever went first, they're not going to go next, right? And then once you pick whoever goes second, now you only have 3 choices left. So what we really are looking at is 5 times 4 times 3. Notice we don't want to do 5 times 4 times 3 times 2 times 1. We don't want to go all the way down. So we can't just say 5 factorial. That's not right. We want to only go down so far. Let's look at another example here with a few more players in this case. You're a Little League coach with 13 players on the team, and you need to pick a lineup of only 9 players. Well, in a lineup, order matters. That's another one of those words. You think about standing in a line, whether you're first in line or last in line or 12th in line, it matters. And if you don't think it matters, then just go to Disneyland. And if you feel like it doesn't matter if you're standing first in line there, then you are a better person than me. So where you stand in line, order matters. Next, it says we have a lineup of 9 players. So I've got my 9 blanks. Keep in mind, I have 13 kids that I could put in that first lead-off starting batting position. I have 13 of them. But once that kid bats, they can't bat again. And they can't go second anyways, like not until it comes all the way back around. So that's why we're going to do 13 times 12 times 11, and then, and then, and then, and then, all the way down to 5. But I need to stop. I don't want to go 5, 4, 3, 2, 1, because I only have 9 available positions. This is it. So there is a way we can do this on our calculator. First of all, we can just type it in. Ooh, there we go. That's a lot. That works. There's other ways to do this though too. And I kind of want you to think about this. We did this a little bit ago. Because if I had 13 factorial, but I just don't want 4, 3, 2, and 1, like I want to get rid of those, one way that I could do that is to divide out that 4 times 3 times 2 times 1. Like I could do this on the calculator if I only wanted the first 9 positions, the first 9 numbers from this 14 factorial, I could actually do 13 factorial over 4 factorial. So 13 factorial divided by 4 factorial. And notice I get the same thing. Now, I don't necessarily expect you to just be like, oh, yeah, that makes perfect sense. I mean, I hope that it does. Like, if you just don't want to keep going, we can just divide them out. And that's fine. But you know, in math, that's such a common thing. We have a notation for that. If you look down here, that looks kind of familiar, hopefully. So we have a formula that allows us to shortcut this. The number of permutations of n items from a group taken r at a time is given by this. And if you consider what we did just a second ago with our baseball players, where we had 13p 9, 13 kids to choose from, and we're taking 9 at a time, right? Well, according to this formula, it's 13 factorial over 13 minus 9, and then we have this little factorial there, which is 13 factorial. 13 minus 9 is 4 factorial. There we go. That's what we got here just by reasoning it through. So there is a shortcut way to do this, and it's to use this permutation. 13p9 is that. Okay, this is the total number of choices or of decisions, and then this is the number of blanks. There we go. So that 13 is the total number of kids, the 9 is the number of blanks. Okay, there we go. Now the n minus r, that bottom part of this, that does represent the elements that are not chosen, right? That's where this 4 comes from. We had 4 kids that didn't make the cut. They just, I mean, we can't play everybody, I guess. So since we're not going to be arranging those elements, their order does not matter. You want to think of this as if we just simply tossed the unused objects on the floor, tossed them aside. Sorry, maybe we shouldn't think about that in terms of kids. That's not very nice. They're going to play the next game, just not this one. So let's do another one here. There's 15 people competing for gold, silver, and bronze medals in an Olympic event. How many arrangements of winners are possible? How many ways could these medals be handed out? Well, I see there's 15 people all competing for these 3 medals. And if we wanted to think about it one way, we'd say gold, silver, bronze. There's 15 people that could get gold. There's 14 people who could get silver, and 13 people could get bronze. Remember, you can't get a gold and a silver and a bronze. That's why the number decreases 1 each time. There's another way we could write this, and that's to say 15p3. Right? We have 15 runners to choose from, and we have 3 medals that we're giving out. So in our calculator, we can do 15 times 14 times 13 and get our 2730. This number is nice, but there's another way to do this, and this is very important. The idea of using this P notation, this permutation, is really common in math, so much so that most calculators have a permutation button. And if you click the function button, it's right there, kind of in the middle, just next to rad. Function button, and then down in the lower left-hand corner, it says NPR. The bottom left-hand corner says NPR. Now, the way that this works is I'm going to write this as 15 and then comma 3, close parentheses. This calculator, this is one of the things that Desmos doesn't make it look just exactly like we write it. We write it like this, 15p3, but in the calculator, we'll write it as NPR and then 15 comma 3. You can see that the calculator still gives us our 2730, which is the same amount as we had before. Don't worry about that NCR that's right next to it. Suppose you're taking a holiday photo and you have a family of 5 and their pet dog. Assuming that the dog will be in the front and center, because some people just think the dog is the most important thing, and that way you can still see him. What we do want to do is how many unique ways can you arrange the entire family of 5 behind the dog? Well, if you said 5 factorial, you would be correct. That's because you have 5 different people could stand on the far left, and then once they're standing in that position, they can't stand somewhere else. So then it's just 4, 3, 2, and 1. Or if you said 120, that's also correct. Or if you also said 5p5, that's also correct. All of these are equivalent to each other. You have 5 people to choose from, and we also have 5 blanks that we're going to fill. So remember, this one is the number of blanks, the one on the right. So 1, 2, 3, 4, 5. And this is the starting number. So 5 times 4, 3, 2, and 1. Now, after you take a few shots with a family and you get one that's good and it's great, then you decide you want to take some photos without anyone standing in the back. How many unique ways are there to arrange 0 members of the family? Well, keep in mind, when we had 5 members of the family, there were 5 factorial. So wouldn't it make sense that if we have 0 members of the family, we would have 0 factorial? But remember, when no one's standing there, we can still take a picture. We just end up with a dog in it. So how many ways can we do that? Exactly 1. You see, 0 factorial, not only do we define 0 factorial to be 1, it also just makes sense because 0 factorial is the number of ways that you can arrange 0 items. If we have 0 family members to arrange, there's exactly 1 way to do that. A picture with no family members in it. Right? I have 0 Ferraris. Right? How many ways can I park my 0 Ferraris in the driveway? Well, how much? Just 1, right? There's no Ferraris there. My driveway is empty. So 0 factorial is 1 because it's the number of ways of arranging 0 items. All right, up till now, everything's been distinct. And what I mean by that is if you look at the TWO that's on the left, right, this. If we want to talk about all the ways that we could arrange these 3 letters here, TWO, I could say, we could make a tree diagram if you wanted, but nah. We could have TWO, TOW. Let's put the W in front. WTO, WOT. Let's try putting the O in front. OWT, OTW. So there's 6 ways to arrange that. And hopefully you thought of this and said, well, there's 3 letters, so 3 times 2 times 1 equals 6. That's easy. We've been doing this already. That's just 3 factorial. But when we look over here at this other one, TOO, well, I could arrange it as TOO, And if I try swapping these two O's and I write it as T-O-O, where I've switched the other two, you can't tell. That's looks like the same word. You see, it's not distinguished. It's not, you can't tell the difference. So we're not going to write it. But I could write it as, I could write O-T-O, or I could write O-O-T, and that's it. There's only three ways for me to be able to distinguish between these. There's only three distinguishable permutations here. So there's a very easy way to take care of the repeated items. First, there's a formula that we have down here, and that can be a little bit tricky for people when they're first learning it. We are going to talk about it. So when items are repeated, their order doesn't matter. You can swap things around, and it's still an identical arrangement. Earlier in the lesson, we actually divided them out because we said they don't matter. So this is the same thing we're going to be doing here. The number of permutations of n items where p items are identical and q items are identical and so on can be solved just with this formula here. Let's jump right into using it though. So if I have, how many distinct ways can the letters of the word bananas be arranged? Well, notice that I have to first identify the n items, or in other words, how many letters there are. 1, 2, 3, 4, 5, 6, 7. So I have 7 letters. This would be 7 factorial on top. The next thing I'm going to do is it says where p items are identical, it looks like I have p factorial on the bottom. So I have, let's see, an A, an A, and an A. Those are all identical. So I'll put 3 factorial on the bottom. It also said look out to see if there's other numbers or letters or items that are identical. Notice that if we have more, we just keep going. So here I have an N and an N. Those are identical. So I will also put a 2 factorial down here as well. So the 2 factorial represents the fact that the N's are repeated. The 3 factorial represent the fact that those A's are repeated. Now it's just 7 factorial over 3 factorial times 2 factorial. We have 420 possible ways of arranging the letters in the word bananas. The last one is the word dilly-dally, which is kind of silly, but I like it because it has a lot of repeated letters. You can do this with all kinds of words that, I mean, you can do it with any word, but it shows off really well in words that have many repeated letters, like Mississippi is also another really good one. So dilly-dally, when we count up all the letters, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll start out with 10 factorial on top. Now let's go through and identify the ones that are repeated. We have an L, another L, another L, and another L. So there's 4 L's here, so I'll put a 4 factorial for all of the L's. The next thing that I'm going to notice is that I have 2 D's. So I'll put 2 factorial down there for the D's. And then I also see I have 1, 2 Y's down here as well. So I'll put another 2 factorial down on the bottom. I think that's everything. Let's just double check. We had the L's. I didn't circle those before. The only thing that's left is this I and this A, and those are not repeated letters. So we're good. We're just going to put this into the calculator and then we'll be done. So I'm really used to my keyboard where I can just use the exclamation point on my keyboard. Now 2 factorial, it's really just 2 because 2 times 1 is just 2. But I'll go ahead and write it here anyways in case there's any confusion about it. There we go. That's 37,800, hopefully. Assuming that I typed it in right. And if I didn't, I'm sure you'll let me know. Well, that's a little bit about counting. As I said, I know that counting seems like it's very easy, but it can get to be kind of difficult. And you run into these crazy things like how many ways can you arrange the letters in dilly-dally? But with a little bit of practice, it kind of turns back easy again. So remember, what we did today was arranging and lining things up where order matters. We'll look at some other kinds in the future, but that's the big key for today is order matters. All right, well, I hope this was helpful, and I hope that you continue counting. Bye-bye.